Okay, so I just want to give a brief introduction here to what's going on. So I want everybody to understand Lab 2 and get the SWIMs working, and if you need any help getting the SWIM working, let us know and we'll come around and help you get it working. A couple of things I want to say is if you've got, like, both lab partners should have everything that necessary to get it working, have your computers working. So while your lab partner's here now that you're together with your lab partner, make sure that you both have the code and you can both compile and run it and make changes to it and run those changes. So what you more or less want to do is fulfill the 3 tenets of mercivity. You know, do no harm to the planet, do no harm to others, including other species, and the third is the other one is the technology. You know, be able to see the technology, see and understand the technology, and modify it. And so read and write permission on the technological universe around us is what the other tenet is about. Really, there's 6 principles because they're bidirectional, all 3 of them. So read and write access to technology. So make sure that both of you can read and understand the code and make changes to it and run those changes, so that you both have read and write capability on that code. And that means you're going to check your computer and make sure. So if one of you has the computer running, because some of you have said, yeah, if you guys want to listen up for a minute, I'm just going to go through a quick intro and then we'll get back to the sessions. So take your code and make sure it runs. And a few people have said, oh, my lab partner's away today. I can't do anything because I can't run the code. So you want to make sure that doesn't happen. Make sure that you can run the code. If any of you need extra swim sticks or anything, last day I had an extra cable I could lend somebody, you know, just to keep things moving along. So that's really, really important. So I want to say that the lab here, we'll post the Instructable and you'll respond to the Instructable. So everyone will upload their code to GitLab. So everybody needs to make a GitLab account and an Instructables account. So you can upload the code to GitLab and also post on Instructables. And what we're going to do is I'll place that in Instructables. I'm trying to apply by the 100% principle, which means I want to give the students who are really sort of keen and interested and kind of really focusing on it, I want to give you the chance to be inspired. I was today, an interesting little side note story is that today in our high school we had a really good math teacher, Ron Lancaster. He was sort of my favorite teacher, really inspiring, inspired a lot of people to math. And he said, thank you, Steve, you were in my mathematics class at the start of my teaching career. I recall I tried to enter a mark of 105% for you, but the system would not allow me to do it. So I want to actually return the favor of trying to enter a mark of 105 or 110 or 120% for some of you and have the system not allow me to do it. So if any of you do get a nice mark like 120% or something, I'll have to enter 100. But what I can always do is write a letter or something on your behalf that the student earned a mark of 120%, which had to be clipped to 100 due to limitations of the system. You know, like that would be a nice letter. I hope that I can be in a position where I'm writing a few of these kinds of letters. So try to be inspired, do something fun. And one of the things that we want to do with this fun is it's a fun art project. This is the mochoid. This is a spinning strip of addressable LEDs on a rope. And what it does is it creates this kind of 3-dimensional display symbol of sustainability. So this will kind of be fun. Maybe Lab 3 will do something, a lot of people have expressed interest in this. We'll do something fun with this. Of course, if you whip it up faster, which I won't do in here, it'll go into other harmonics and start to whip around wildly and create beautiful patterns. Not exactly a Fourier series because there's gravity applied to it. Try to think what you've got happening here. Try to write a mathematical expression for this shape. That would be fun. So you know you've got centrifugal effects pulling outwards, and you've got gravitational effects pulling down. So you've got, consider a small mass m upon that rope. You've got m omega r squared pulling out, and you've got mg pulling down. If it's a chain, like I've got one that I made out of a chain, 64 links of chain that weighs 100 grams. So each chain has a certain mass, each link has a certain mass m. It's really obvious there. You can imagine a small increment of mass on here, dm. So you've got mr omega squared pulling out and mg pulling down. You know the force, the tension in the rope is f sub t, and so we know Cartesian coordinates, f sub t cos theta equals mr omega squared, and f sub t times sine theta equals mg. So there you have a very simple set of coupled ordinary differential equations. Should be able to solve that, write down an expression for this shape. So it has a certain mathematical form, the shape here. And of course it depends on the speed and everything. As I spin it faster, we can weigh the rope, you know how fast it's turning, we know how much the rope weighs, and we know therefore the mathematical pattern that it follows. And this is the fundamental mode, of course. And I call this the mochoid. Mo is in, you know, motor. The first two letters of words like motel means motor hotel, and from the word move or movement, which is where the word motor originates from. And so it's a motory, motational chord, as in chordophone, the Greek prefix for string musical instruments. The original ones I used to make were musical instruments that spun around with spinning strings and stuff like that. So that's kind of where I started all this. So the mochoid, and oid as in ellipsoid or cardioid. And so it's a three-dimensional shape, but we can make a simple mathematical assumption and assume that it's in a plane approximately. You won't be too far off if you solve a set of differential equations that assume that it's just a two-dimensional problem. It'll be pretty simple. I can share, and any of you want to share on this Google album, be happy to share it with you. To see here, here's just the write-down of the mathematics I just went through, and then here's a couple of examples of what it looks like. So I've got on there a beach scene with clouds in the sky and beach. So I took a beach scene from Michael Hoff Beach.
Different picture.
Say again?
It's not the beach picture.
Say again? Yeah, this one is a different one, but some of these are the beach scenes. So if I go to the, depends, sometimes I just put a blue pattern in there. These are some of the other modes. There's one, there's the beach scene with the clouds and everything in the sky. And that's whipping through a couple of different modes. So as it gets more energy in it, it goes into a higher mode. You notice it's not symmetrical, it's not just sines and cosines. Gravity has an influence, so it's pulling down. But it makes an interesting shape, it's an interesting mathematical function. So I'm hoping that lots of you will have a chance to have some fun with this. Now, if we want to see how that works, we can look at that. And so now we have to, when it's spinning like this, you've got to somehow get power to it. So one thing we can do is mount a microcontroller on the end of that and put a battery on the end of it that spins with it. Or we can use slip rings. On this one I've got slip rings that convey that, and the computer system's mounted in that roll cart with the hydraulophone together using the same power supply as the water pump on that hydraulophone. So now, right now, I'm at 15.3 volts. And so we can make a note of that, and we could photograph this and measure the RPM. You could count that. You guys know how to measure how fast it's going? So time it. Grab a stopwatch. Anybody here got a stopwatch? I'll just show you quickly how to calculate omega and time it. So we'll go 10 turns. So we'll go go 1, 2, 3, 4, 5, 6, 7, 8, 9, stop. 15 seconds. Okay, so that's 1.5 seconds per turn. So you can calculate, you know, the speed of that. Beautiful. So now, if I wanted to play that, what I would do is I'd take the end of this. I'm just going to take it off of here. You can easily conceptualize how that will run. But I wanted everybody to see this thing in action. And I got a little platform so I can stand in the center of it too, which is kind of fun. What I've got here is I've got bearings with a pipe. There's a pipe fitting here. So this pipe doesn't turn, this thing turns around, and the center doesn't turn. And that allows, it makes it easy to put a platform on here that I can can stand on, for example, while it's going around, and the platform stationary, which is just kind of fun. So now I've got this light rope. This light rope is, the length of it is 5 meters. And as a general rule, I find aesthetically, artistically, I like to have about 12 and a half feet. So 2.5 times the length, 2.5 times distance, height in feet is 2.5 times the length in meters. So if you got a 10-meter rope, you want to have 25 foot high mochoid. 5-meter rope, you want about 12 and a half feet high. This ceiling's not high enough. I would sooner have this be about 12 and a half feet high, roughly. That's just an artistic decision, but you know, it'll come into the mathematics of the form the shape takes. Now usually on these ropes and on these devices, the white is ground, which I connect with a black wire. The green is clock and data together, which I connect with a green wire. And the red is +5, which I connect with a red wire. So then I've got this connected to the rope, and if I plug this into my computer, and this is just the S.W.I.M, this is the same thing you guys have. If I plug this rope into the computer, which is kind of a nice piece of here. Now there's my beach scene with the clouds and everything. It's clocking through there. And so I just took a photograph of Michael Hoff Beach. And what I did is I encoded it to save data space. Instead of RGB, I encoded it 1 byte for every pixel. And so I used 3 bits for red, 3 bits for green, and the remaining 2 bits for blue, because the eye's not so sensitive to blue. Of course, if your scene has a lot of blue and water in it, you could also jiggle that around and maybe use 3 or 4 bits for blue even, and less for the other colors, depending on your subject matter. But in any case, that way it compresses it down, because you only got 4 megs. So you got to use it wisely. And one decision I made was to bash it down a little bit and use 1 byte for every pixel with a reasonable enough color fidelity, because it's kind of a lo-fi image anyway. There's only 50 pixels per meter on this rope, and it's sort of relatively low fidelity. So I wanted to make that simple. And then this is the, so you can see it there. I'll just set this down on the ground here. And now it's really short and sweet here. So it's just using fast LED. You can look here, and this is the image array. So it's just a text array, just for simplicity. It's just in the source code, it's a text, and it'll just compile directly into that array. So it's really simple. Now, you guys are fancy. I'm sure a lot of you are going to, use a bit more of an advanced approach and probably have an image and read the image and everything. But this is just fast. This is just a quick 5-minute hack to throw that image out the port there with a delay. And there's a contact closure here. There's a little Hall sensor. There's a Hall effect sensor. I've just got a magnet stuck to that pipe there with a little Hall effect sensor that whizzes past it. And so this will just pick the contact closure. This is just dead simple. Every time it hits that contact closure, it plays out the image once and then stops. So that's pin 5 of the controller. So pin 4 is the clock and data together, and pin 5 is where the Hall effect sensor is connected. You probably want a push button on your thing anyway, because you'll want to be able to push it once or keep it pushed all the time. So you could jumper it and let it just free running so the image repeats. But in all likelihood, you want a push button. So when you push it once, and even if you let go of it, the image plays out till it's done and stops. And if you hold it down, the image just keeps playing. And you want to put a delay or a space between the image. You probably don't want to run the images one right against the other. Maybe you want to space them out, especially if it's your name. You want space between letters, let's say, and then you want a long space and then the next occurrence. So it might say Ben, 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 Ben over and over again with a space between the bends if you hold the switch down. And if you just push it once, it'll say Ben once and then it'll stop. So that way it'll give you the ability to create some fun art when we play in the lab. So hopefully our lab will be like a fun day of making some fun visual art and getting you guys some nice profile pictures that you can use that are really fun and cool. So this has got 200 LEDs in it. Typically we define the number of LEDs in the array. And what we've got is that array, and then there's an octave script that you can in this case, let me just show what that octave script is. Packimagedata.m. It's really short and sweet. All it does is it IM reads the thing you want to read, whatever the PNG is or whatever image array, and then packed image. You can see this is a one-liner. I just came up with a short one-liner here. Look at that for a second and see if you can catch that. But start by experimenting a little bit. But it's basically just, I found different numbers that if I divide it by, multiply it by, it packs it into, it happens to pack it into the first 3 bits for red, the next 3 bits for green, and the next 3 bits for blue, and then it prints F. Print F %D packed image, just prints it to standard out, so you could put diary on an octave, go diary on, run this, and then just puts it out, cut and paste the thing, stick it into their Arduino code, fast and dirty, not very elegant code. It's not a very elegant way of doing it, obviously, but it's fun and simple. Just get it done quick. And then if you want to be fancy, you can start to do more fancy things after that. So that's kind of where I'm at, and then what I want to do is come around and give everybody a little bit of help here, but I want you to get inspired and realize that this is a lot of fun, and it can be a lot of fun. And think creatively, what could you do with this? Could you spin this around in some fun way?
You could mention you connected to that S.W.I.M instead this time. Like,
say again?
you could mention that you connected to the S.W.I.M.
Yeah, this you mean this thing here?
Yeah.
Yeah, I just connected this rope to here, right? So that's all I did, is I just took this S.W.I.M here and I unplugged the breadboard from the S.W.I.M and plugged it into this piece of rope. So if any of you guys want to play around, I got lots of these ropes. If some of you are really into some fun and you want to borrow a rope or sign out a rope or a longer S.W.I.M or something, I got some really long S.W.I.Ms. I got a S.W.I.M in my office that's 2,200 LEDs.
Come on, Ben.
Good power supply, right?
Yeah, you need some power as the S.W.I.Ms get bigger and more dense, right? You'll need power. Like, you don't want to sagging. Some of them you got to power them at both ends. You need a separate power supply. This is simple. It's all being powered from the breadboard. Even this one's simple. It's only got 50 LEDs per meter, so this thing only has 250 LEDs in it. And so I should really use a 250. I was just using a 200 array because the S.W.I.M that I had before was one that had 200 LEDs. This has got actually 250, so then I'd use a bigger array. So you put your image array. You're going to hit that 4 meg limit pretty quickly though. So you're going to want to one byte per pixel makes sense. If you really want to get fancy, write a JPEG decoder on the fly, but that's getting unnecessarily fancy. The other thing is compression. I was starting on a zero length encoding, ZLE, instead of RLE, because most of this stuff we're doing is all black-grounded, right? Just about everything we do in a backography in this form of this art form of computational light painting, or what we call a backography. In this world of art, everything's black-grounded. So I use black screens. I don't use green screens. I've been using black screens. I got all the walls painted black. I usually wear black. My wife just got me this brightly colored shirt because she thought if I'm jogging or cycling, maybe the black isn't the best color. But usually black is my first choice. And the thing is, everything's black grounded. So you've got your image array, your content is all in a black background. So it's mostly zeros. So most of the array is zeros. You don't have to encode runs. You don't have to bother with RLE. You don't have to bother with, say, I'm going to take a run length of so many. You guys all know what RLE is, right? Run length encoding. We take a certain number of identical pixels and pack them down. But you don't need to bother with that. Just do zero length encoding. It's a lot easier. ZLE. So you can take your array and count how many zeros there are, and then put that number of zeros. And you just save one value, like scale your image instead of 0 to 255. scale it from 0 to 254 or from 1 to 255 and save one byte value to represent 0. And then the following byte is how many zeros there were. So if you had like 200 zeros, you would go like the special byte and then the number 200, and then it knows that's 200 zeros. And that'll bash your image size way down because most of it's backgrounded. So you could try that as well if you're doing imaging. See where the limits are. See when you do hit that 4 meg limit. You can always put an SD card reader on here and put a huge terabyte CF on there, right? Or SD card and put the image. But it's a lot of trouble to hook up an SD card. It's far easier just to compress your image down a little bit, do something clever. Happy to award bonus marks for clever things. I'm hoping that some of you, Ben, Emily,
Adrian.
Mindy,
Adrian.
Hmm?
Adrian.
Adrian? Yeah. And Aaron. And good. There's some of you are very likely, I think, to be on that past 100% point where you're doing something cool and fun. So yeah, let's. So tomorrow is in the Bayan Center. Tomorrow's class is in the Bayan, or not the Bayan Center, in my hall, in the My Hall Center. Tomorrow's class is in my hall, Makerspace. So anybody else need help with making, physically getting your thing ready? I'll be happy to help you get it ready, picture perfect ready. Make it look nice, get it neat, get your thing into perfection for Thursday, because Thursday's show day. You're gonna come here, do some nice photographs. So dress it up a little bit, come up with some ways to make it look really cool, wire it nice and neat, get it looking really good for Thursday. It's almost like showtime. So tomorrow we'll be in the makerspace. If you guys need any help, does anybody else need more swim sticks? I do have extra swim sticks. I can give you the CAD file. My CAD file, I had them butted up right against each other, so as it cuts through, if the laser cuts twice along the same line, it'll leave a lot of charking or burning. So if any of you want to space them apart a little bit, evenly space them apart so that they're cut neater and do another run as well. That's great too. I sent out the CAD file. Let me know if you guys all have it. If you don't, I can send it again. I can get you the CAD file and maybe make some design revisions and come up with something cool. We're in the makerspace tomorrow, might as well put it to use. All right.